Okay, so, well, thank you for inviting me. It's great to be here. Glad it's a bit cooler today than it was yesterday. It was a swelter yesterday. So, just SDR explained is a bit of a big title, really, because it's asking a lot to explain it. But I've been to lots of explanations about SDRs, and they very quickly dissolve into some fairly high-tech maths. And I'm not into high-tech maths. So what I've done is put together a presentation which keeps it a bit simpler and explains the principles. And what I'm trying to do here is to let you better understand what happens inside an SDR receiver so you can perhaps use it more effectively and understand what you're doing when you're altering controls, etc. So let's start off by what do we mean by an SDR? And basically, sorry, that's what I'm going to talk about. So the basic principles, some types of SDR, and a bit about next generation in SDRs. So when we talk about SDRs, it's pretty broad, to be honest. Early SDRs were where some part of the signal was handled in software, and that can range right through to where everything from the antenna is digitized. Okay. So there's a huge range of different types of software-defined radio. But to understand SDR, there's a few principles we need to understand behind them. The first is about in-phase and quadrature signals as to why they're important and why we use them. The second is the analog to digital conversion process, which is at the heart of SDRs. And also a bit about decimation or downsampling, how we downsample the signal. And then finally, fast Fourier transforms, which is how we get these wonderful spectrum displays that we all enjoy these days. I can't imagine life now without a spectrum display. We got so used to it. So probably your first amateur radio encounter with SDR would have been with the Soft Rock series that came out a few years ago. So these were direct conversions where the RF is mixed straight down to the audio range, using a carrier oscillator that's at the same frequency as the RF signal. Now, in a soft rock, you have two mixers, two identical mixers, but the difference is that the carrier oscillator, one is in phase and the other one is out of phase by 90 degrees. And that makes up a quadrature sampling detector. But you've got two signals. You've got an I signal and a Q signal comes out of that. So why is that important? It's the same signal. You're just shifting it by 90 degrees. So why does that work? So we need to understand that. The first thing we need to appreciate is most of the measurements that we're used to when we look at RF signals, like your oscilloscope, etc., they're two-dimensional measurements, okay? But our 3D signals are three-dimensional. So if you look at, here we go, there's a sine wave, but if you turn it around and look at it from another dimension, it's actually a spinning wave, okay? But you don't see that on a, let's see if we can go back on that and show that again. Whoops. So a sideways view of a circle, a helix, looks like a sine wave, but we don't ever see that. But we need to know that in order to demodulate signals in software. So the important thing about the IQ signals is that it gives a 3D view of our signal, and it's at the heart of all SDRs. Every SDR uses IQ signals at some point in the process. A common way it's used is, you know, the little rotary encoders you've got on all your transceivers these days that just go round and round and round in place of volume controls and multi-way switches. Well, they work by having a common pin and an A and a B pin. And when you turn it clockwise, the A pin pulses before the B pin. When you turn it anti-clockwise, the B pin pulses before the A pin. And they're in quadrature, so you can tell which way it's going by looking at these pulses. And it's exactly what we're doing with I and Q signals. And the easiest way to show you what happens and the power of IQ signals is to look at SDR modulation. And we can make a little test circuit up. In fact, I did this just to prove it with a couple of mixers and a combiner. So here's what it would look like. So I used a couple of mini circuit mixers, double balance mixers, and an SI 5351 oscillator, 0 and 90 degree out of phase, and put them through a combiner, and you get an output there. So we're going to look at what happens here and what happens there. So if we put identical values in the I and Q signal, like so, that's the I signal, that's the Q signal, so they end up 90 degrees out of phase. If you add those two together, that's the output here, this is what you'll get. Not a big surprise, the difference between all those two added together produce another sine wave, but it's just 45 degrees shifted. It's exactly the same frequency, it's just shifted by 45 degrees, because you're dealing one at 0 degrees and one at 90. So, what happens if we just move the volume or amplitude of the I and Q signal together? Not surprisingly, the output just goes down to 0. But that shows how we could do AM modulation. So if we've got those two mixers and a carrier oscillator, and we apply the same audio signal to the I and Q ports, the output will go up and down, it will be AM modulated. So we've got an AM modulator just by altering the I and Q signals. So it's really easy to do, to create AM with I and Q signals. So what happens then if we start altering the I and the Q separately? So let's look at that. So what happens if we reduce the Q signal to 0? Here we go. So, whoops. So you see that our output sine wave moves this way, and it moves this way by 45 degrees. So what happens if we move the I signal to 0? If you watch the sine wave at the bottom, it moves to the right 90 degrees, at 45 degrees. So what that means is by altering the I and Q values separately, we can shift the phase of the output signal. So now we've got phase modulation we can do just by altering the I and Q signals. So by changing the values of the I and Q independently, we can do phase modulation. By doing them both together, we've got amplitude modulation. But we can also use, I only showed positive values for I and Q, but we can use negative values for I and Q as well. And if we do that, we can create phase modulation using I and Q signals, but we've got the whole 360 degrees available for us, which means we can do frequency modulation, because that's just a version of phase modulation. So I'll use these IQ plots just to show you the potential. So these plots, the vertical axis is the Q signal, horizontal axis is the I signal, and the output you just plot from whatever the I and Q value is. So that line there is how large the output is, i.e. the amplitude, and that is the phase of it. And this is our 360 degrees all around here. So you can see with positive values, you could put this dot anywhere in this quadrant by changing those values. So if we change over and go to a negative I signal, we can put the dot anywhere in this quadrant. If we move on to them both being negative, we can put the dot anywhere in this quadrant, and finally anywhere in that quadrant. So by altering the I and Q signals, we can create any form of phase or amplitude modulation. So that's why I and Q signals are just so powerful for SDRs. And the great thing is it works in reverse. So if you put a modulated signal in there, the I and Q signals, the phase changes will be able to be extracted. So you can demodulate any signal. And we get back to the soft rock, which is this quadrature sampling decoder. So the point about this is that IQ signals are really powerful because they allow you to create any modulation system and demodulate any demodulation system. So it's why they're at the heart of all software-defined radios. The actual business of mixing, the mixers that I showed you there, although I did the experiment with little mini-circuit mixers, you can do that whole operation digitally in software as well. You can replicate it and it works exactly the same. So now let's move on to the analog to digital conversion process. So computers can only handle binary numbers, so all you get is ones and O's to deal with. And so to convert a radio signal into ones and O's, we have to make measurements, and we make measurements very rapidly, voltage measurements of the signal. And you have to sample at a rate that's twice the highest frequency or bandwidth you want to sample. So for example, if you want to sample the whole of the 30 megs band, you need to measure at 60 million samples per second at least. So that's a hell of a lot of samples you've got to take. So here's just an illustration of how it works. That's our radio signal, and then we would just sample at regular intervals. And it's just taking a voltage measurement, and that produces a long string of serial data coming out, which is all ones and O's. So that's how the process works. Now, when we make our voltage reading, you can imagine we're using a voltmeter, but we're using a digital voltmeter, and it's only got so many increments on its scale. And the number of increments on that scale are determined by the number of bits, digital bits in the ADC. So a low end, like a SDR dongle, will only have 8 bits in its SDR. So there'll be 256 steps between 0 and 255. If you convert that to dBs, that's a range of 48 dBs between the weakest signal that it could possibly deal with and the strongest that it could deal with. If we start going up, 12-bit is a bigger number, 14-bit is an even bigger number, and the standard that we would use for things like flex radios and all the rest of it is 16-bit. So there you've got 65,536 steps between 0 and the maximum that it can handle, which equates roughly to 96 dBs. So that's much more useful. So the resolution is really important. So generally speaking, the more data bits you've got, the greater precision and the greater the dynamic range. And that gives you the difference between the weakest and the strongest signal that it can handle at the same time. Okay, that's an important point. But real ADCs offer less range because there's noise at the bottom of an ADC and there's distortion created by the ADC process. So you don't see that full amount. And the way they're often measured is using a term called ENOB, effective number of bits. So it's how many bits has it really got after you've taken out the noise and distortion. And it's quite a big drop. So typically, this is a popular ADC for direct downsampling transceivers, etc. A 16-bit ADC has only typically got an ENOB of 12.5 bits, which is quite a loss. But we can improve this later in the process. So the trick with analog to digital converters is to manage the input. So if, for example, we've got a 8-bit, 12-bit, 16-bit, and that's our range of possible inputs, how are we going to handle that? And the way we do it is we put a variable gain amplifier. Can you just mute this a minute? I need to cough. Okay, so we put a variable gain amplifier in there, and the types that are used can add attenuation as well as loss, okay, as well as gain. So they have a wide range. So the idea is that we can put that ADC's potential wherever it's needed in the range of input signals that are coming in. Now, one of the things we need to consider with analog to digital converters is the amount of data coming out. So I showed you that string of ones and O's coming out of the analog to digital converter. So the amount of data is the number of bits times the sample rate, which gets to quite big numbers. So just an ordinary 8-bit sampling at 10 megabits a second, or mega samples a second, will give 80 megabits of data. But if you go up to the high-end SDRs, like a flex or similar, then you're talking about 2 gigs of data coming out of the analog to digital converter. And that's a hell of a lot of data, but not only have you got to be able to transfer it, you've got to, thank you, you've got to be able to do calculations on it as well. So it's asking an awful lot. So it is a lot of data to process. So let's just summarize this. So to digitize our signal, we sample it and convert it into a digital data stream. The data rate depends on the sample rate and the bit depth. And the data rates can be extremely high, scarily high sometimes. So I'm going to move on to another bit, but I'll come back to data rates in a minute. Now, spectrum displays are the things, probably the biggest change that SDRs gave us is when we got spectrum displays. Because all of a sudden we could see all the activity on the band and be able to jump about quickly and find what we want. So how do we convert this string of bits that are coming out into a spectrum or waterfall display? Well, we use a basic principle called around the Fourier series. And that says that any waveform can be constructed by combining multiple sine waves. The good thing is, and Hammond organs use that principle, I suspect you know Hammond organs have got tone wheels inside, or always used to in my day, and produce basically sinusoidal tones out of them, and you use the drawbars to mix them to make all sorts of interesting sounds. Same sort of thing with church organs. Well, the Fourier series lets us disassemble a complex waveform. So that's what we're going to do. And the way it works is like this. So it takes a sample of a signal, which is just a whole load of ones and O's. It then puts it through an FFT, which is a computer algorithm, and the output gets put into these separate bins, showing the amount of power in each one. Now those bins in this case are 330 kilohertz wide, and the signal level is indicated by the amount of signal that gets allocated to those bins. Now you will have seen on your receivers and transceivers an option to choose the FFT size, and the size determines how many bins there are. So how fine a resolution. So the bigger the size of the FFT, the more resolution you get. So if we had a 10 megs bandwidth and an FFT size of 10, we'd have a bin size of 1 megahertz, which is really soft and won't tell you very much. So practical systems always use the power of 2. That's why you get these types of numbers you'll see. When you step through the options for your FFT size, they're always powers of 2. That's because the algorithm works much better with powers of 2. So an FFT is iterative, so it does the calculation lots and lots of times. It does it every time for each bin. So if you've got thousands of bins, it's got to go through and calculate all that. So it's heavily process intensive. So whenever you increase the size of your FFT, you will probably notice that your display update gets slower and slower. So you get more and more detail, but the display updates more slowly, and that's because there's more processing required. So the faster a PC you've got and the better graphics card you've got in your computer, then you will get a faster update. So that's just a summary of it there. So associated with FFTs, you will have heard windowing spoken about, so Hamming and Blackman and various other types of window. And I don't think a lot of people understand what a window is in this respect, so I'll try and explain it here. So when we run an FFT, we take a sample of all that data stream, which is all those ones and O's, and we take that sample and we take it out and then we work on it. But the FFT works in a loop, so you have to connect the end of that sample back to the beginning, and then it processes that loop. If there's a discontinuity where you loop the end to the beginning, then it's like a key click, and it will screw up your FFT. It produces smearing. Real signals don't match when you put the two ends together, or rarely. So a window, all it does is reduce the end of each sample down to 0 before they're joined together. So that if both ends are at 0, you know they're going to match, so you won't get the key click. So here's an illustration. So if that was our sample to be analysed, if you look at that, if we join that end to that end, we've got a discontinuity. So there'd be an immediate step, which would be like a key click, which would smear the spectrum. So what we do, we put it through a filter which looks like this, for example. So it turns our sample to be like that. Now we can join the two ends together and there won't be a sudden discontinuity, so it will work. So this is the sequence. The signal to be analysed, we take a sample, we put it through a window, we apply the FFT, and then we get a display. And then we go back and get another sample. So that's your display update. So when you see your display updating, it means it's been through that process and it's now going back to get another sample. Through that process, then getting another sample. So again, the bigger your FFT size, the slower that process will be. So we use the FFT to display the spectrum of the captured signal. The size determined by the number of bins and the display resolution. Larger FFT sizes increases the load-in and slows the update rate. So now let's move on to decimation. Decimation is really the wrong term because decimation is actually reducing by 10 times, and normally we're not reducing by 10 times, so downsampling is really the right term for it. But the two get used interchanged. So while having a wide spectrum display is nice, it's not always very useful, and it's not the most useful thing. When it comes down to demodulating a signal, we probably only want 24 kilohertz of bandwidth. We need to reduce that. So how do we do that? So we go back to that business with the top-end ADCs and their 2 gigabits of data. You've got to process that somehow, and we want to downsample it so we can use it. What most people, or most receivers do, or transceivers in fact, they use a device called a field programmable gate array, which is a block of thousands of integrated circuit, thousands of gates and transistors that can be programmed to take on all sorts of different functions. And it's very, very fast because it's all together. And it also does parallel processing, so you can ask it to do lots of things at the same time. And what it does for the downsampling is it discards some of the samples. So it might discard every other sample if it's downsampling by 2. It'll discard every other sample and then filter it to reduce the nonsense you get around that. And it keeps going down until it gets down to the bandwidth that you want. The FPGA also normally creates the spectrum that you see. And then once it's downsampled everything, the result is fairly low data rate, which goes over the USB port to your PC, or in some cases over an Ethernet network to your PC. So one of the things downsampling allows is what's called receiver slices. So this little narrow band part of the spectrum is actually a slice out of the full spectrum, and that receiver slice can be tuned anywhere. And you'll find on some of the better ones that you will have more than one receiver slice. So you can have 2 completely separate units running in the same ADC data. So just taking it again that the raw ADC samples are too hot to handle, basically. FPGAs provide the answer. They reduce the sample rate and they produce the FFT display data. And they provide narrowband receive slices, which you can then process in a PC because they're not very strenuous. Now, the other thing that downsampling gives you is what's called a processing gain that increases the dynamic range. And if we use the Flex radio as an example, the latest, the 6700 I think it is, they run their ADCs at just over 250 million samples per second, which is really fast and much more than they need. But the reason they do it is because you can downsample, and they typically downsample to 24,000 samples per second, and that gives a 40 dB improvement in the signal-to-noise ratio over the bare ADC. So you put that together with their 16-bit ADC, and you get something like 112 dBs of dynamic range from that without any other aid. So it's a very powerful process, and most of the direct sampling systems will use that sort of dynamic range gain, which is a processing gain. In some ways, it's similar to the gain you get from filters. So if you're listening to CW, you filter down from a 2.8K SSB bandwidth down to 500 Hertz for CW, for example, and that reduces the noise that you hear because you've thrown all the other noise away, you've excluded it. It's a similar sort of thing here that's going on. As you downsample, you get rid of all the unwanted stuff from all the other sections of the spectrum. So yeah, that's the example. So a 16-bit ADC is typically 12.5 bits of effective bits, 72 dB range, 40 dB of sampling gain, and you get around 112. So that's enough of the technical stuff. I'm just going to go through a quick summary of the receiver types. The first one is, I'm sure you've all probably got one in the shack, an SDR dongle. They're very popular. They've been about for a long time, and they're a very basic SDR receiver, but they're remarkably powerful. And the latest versions, the RTL SDR blog version 4, which is an odd name, but that's what it's called, is probably the best of those cheap SDR dongles at 25 quid or thereabouts. It's got a lot in it, as you can see. So it's got a Raphael tuner here, an 820 tuner, and then that's the digital conversion. It's only 8 bits, but they use some clever gain control to make the most of that 8 bits there. And when you look inside it, it's absolutely packed with stuff. The latest ones have got a 1 part per million TCXO in them. They've improved the power supply, they've done lots of things to make them better, and they're quite reasonable little receivers now. And the very latest one, the version 4, has even got an HF converter in it, so you can receive HF on it. So another one that you're probably all fairly familiar with is the SDR Play. It's based on the little Myrix TV radio tuners. That was the same as Howard used in the FunCube dongle. But they've done a hell of a lot of work that at least one of the engineers, if not 2 of the engineers from SDR Play, used to work for Myrix, so they know the chip very well, and they've done a great job of extracting about as much as you can possibly get out of that Myrix chip. So it works very well. That's what one looks like inside. You've got lots and lots of filtering. One of the things that these suffer with is overload from out-of-band signals. So if you don't provide a lot of filtering, they really struggle. So as well as controlling the gain very carefully, you've got lots of RF filtering before it gets to the receiver to try and keep all the spurious stuff out. And that's what, I can't remember which one that is. I think it's the 2. But all of this lot is filtering. That's the receiver chip down there. This is all filtering. Another one in the same price range is the AirSpy. It's very popular. It does VHF basically. It does a pretty good job of it. You get a 9 meg spectrum view. Looks like that tiny little thing. It's packed with stuff. It uses the Raphael tuner, which is the popular one, which works surprisingly well, and Yusuf, who designed it, has done a great job of getting the best out of it. His pet design that he worked on was the Discovery HF Plus. Now this was a completely new design, with nothing else like it on the market. I don't think I've seen anything else in the amateur market that does it. It uses end-path tracking filters and a polyphase mixture. I'll show you what that looks like in a moment. And it's got really excellent performance from LF through to 31 megs and 60 megs up. It's got lots of pre-selection filters. This is what it looks like, and the unusual thing is it's got tracking bandpass filters here as the RF signal comes in, and this mixer, which has got 16 mixers in it, and it's fed with a oscillator of 16 different phases, and then it reconstructs the I and Q signals on the other side. What makes it really useful is it works very well with these filters, because although these tracking filters are extremely good, they let harmonics of the tuned frequency go through. But this mixer rejects harmonics of the tuned frequency, so the two work together really well. This is the latest one from AirSpy, which they've announced, but have not launched yet, because Yusuf's having a few manufacturing problems. But I've had a prototype to play with, and it is really good. This one covers from half a kilohertz to 1750 megs continuous. So it's got a very wide range, and when I was playing with it the other week, it's very, very good performance on it. He's basically taken the HF Plus design and improved it with a whole node of new filtering and a completely new AGC system. So that one's one to look out for in the coming months. So if we look at high God, this is an awful buffering. Yeah. How's that? Okay. So when we move to high-end SDRs, the Flex and the Anand are probably good examples of dedicated SDRs that have not come the conventional route, if you like. So they do a direct sample of 0 to 60 megs, and they sample as close to the antenna as they can realistically get. All the processing is handled in software, and they support multiple receiver slices within the rig. And they use FPGAs to handle all that data. And then they put out fairly low rates over Ethernet or USB. So this is the Flex 6300's hardware. A very simplified view of it. So you've got antenna switching at the front end. You've got some filtering, a preamp, a 54 megs low pass filter, because we're only interested in everything below 54 megs. And then a 16-bit ADC. This one was running at 122 megs, which is the 6300. I think the 6700 runs at 250 odd. A big FPGA to do all the hard work, and then you're away into the low frequency stuff. So it makes a very simple architecture, and the thing can be completely transformed by changing the software that it runs. So it makes it very flexible. So if you want to add a new band, a new whatever, it's easy to do. New modes. That's the big attraction. So what about what comes next with SDR? Well, one of the things that's been proposed and is already started is to get rid of the FPGA, because the FPGA is very expensive on its own, but it also requires dedicated programming skills, because it's a completely different programming language to set it up. So the plan is to get rid of the FPGAs. And the reason that's feasible is because now we've got USB 3.1 and 3.2, we can now do high-speed data over USB quite easily. So we've got 10 megabits is relatively easy over a USB 3 port these days. So this greatly simplifies the hardware, because all it comes down to is you're using a digital sampler at the front end. Everything else is in hardware, in software. So all the processing can be done on the PC. Another thing that's made a big difference to making that possible is graphics cards in computers. So graphics cards have got very sophisticated. I mean, you can easily pay £1,500 for a graphic card these days. And they have got very sophisticated processors that do parallel processing. So they'll have hundreds of cores of parallel processing capacity that can do these FFT algorithms for us. So one example that's been around and available to amateurs is this one, the RX888 Mark II. It was costing about 175 quid, something like that. And it does LF to 64 megs, 16-bit direct sampling. And it just packages it up and sends it over the USB port. And it includes, the Mark II includes a programmable game preamp. The Mark I didn't, and it's not so good because of it. Accepts an external clock, etc. It works with HD SDR, it works with Simon Brown's SDR console. He's got full support for it. And I think there's a few other programs that support it now. And this is what it looks like. And as far as HF is concerned, the only bit that's involved is the bit above here. This is the preamp, gain control amplifier. This is the ADC, and no, that's the ADC, beg your pardon. And this is the USB chip that gets the high-speed data out. So it becomes a very simple device mechanically. Now, I'm not sure I recommend you buying one of these, because a lot of these were made with second-hand parts because they came from China. China's got a bit of a history of doing this sort of thing. So a lot of these were built with second-hand parts. But mine is fine. Lots of people are fine. Some people have had trouble. So you just need to, if you're thinking of getting one, just regard it as an experiment, and it might go wrong, but it might be worth a try. If it works, it's fine. Okay, I think I'm nearly done. That is enough. Okay, any questions? That was a bit of a burst through that. I'm not trying to do it in time. But yeah. Don.
Thanks, Don, G3BJ. That last 888 Mark II, I know you weren't recommending it or anything, but because it's moved a lot of the processing into the computer, does that have implications for the specification of the computer? I mean, are we talking about really, really fast PCs to use one of those?
No, it's surprisingly not. Most computers have got really, really fast these days. So an i5 computer, i5 processor will do it quite happily. Say an i5. Certainly an i5 10th generation Intel processor will do it fine, which is probably a standard workstation if you were buying one these days, something like that. Graphics cards help, but you don't have to have a top-end expensive graphic card. A sort of a £200 graphics card will do it. Something like a G4 1650 will be fine. And you can pick them up on eBay for about 100 quid. So it's, so the processing requirements are not that bad. It's just that because computers have moved on so much, and we've got this big fat USB port now that can handle the data, all of a sudden we don't need an FPGA. So, yeah, okay. Yes.
Mark M0KYB. Thank you very much, Mike. That was an absolutely excellent presentation.
Okay.
Really enjoyed it.
Good.
What do you think is going to happen in the future with these SDRs? There seems to be, obviously, there's a lot of emphasis at the moment on AI, artificial intelligence, using NVIDIA processors, parallel processing. Some people are already experimenting with squirting the signal up on the internet to some massive servers, have parallel processors producing noise reduction and squirting it back down the line to the radio. And at the moment, there's a very slight delay with that, but I can really see the whole SDR world perhaps going that way, you know, moving the processor up in the cloud and then bringing it back down again. Be interesting to hear your thoughts on that.
Yeah, you could do that once you've downsampled. You couldn't do that with your 10 gigabits of data coming out, or your 2 gigabits of data coming out. But you could do it once you've downsampled, because, you know, I mean, my broadband at home is 900 megs download and 300 up now, so it would be quite easy to send data up and down. So that is possible. If you take what's going on in the photo world, perhaps as an example, because I do a lot of photography, I've recently bought a new program that does noise reduction, because in photography we've got noise problems, because if you use high ISOs or do low light photography, you get lots of noise in the which is exactly the same as our noise. And there's now AI programs that do a phenomenal job of noise reduction on photographs. I couldn't believe the results. So I can't see any reason why they couldn't do an equally good job on a channel of an amateur radio signal, or any other radio signal for that matter. So it's quite feasible. But what it might also be is, because of all the processing power in your computer, you might have AI in your computer software that's used to reduce noise. So I know people are experimenting with that, but it's a likely way to go. It seems the obvious way to go, because if you think about it, like with a photograph, or when you listen to your radio, you can identify the noise. You can hear it dead clear. You know exactly what the noise is, and you can identify the signal. So all we need to do is teach a computer to learn the difference between the two. We can do it, so we ought to be able to teach an AI computer. Bearing in mind, it works on thousands and thousands of experiences to work out how to do it. I can't see why a computer can't do really good noise reduction. And then you get into cheating, don't you? You know, which is what we've had with photography, where, you know, you can go on one of these websites and ask for a picture of a young girl on a beach at sunset, and it will generate one based on its experience of seeing lots of photographs, etc. So there's all sorts of dangers with it, but it's interesting. It can be very useful. The noise reduction bit is really useful from photography. I recently did a wonderful trip to Zimbabwe, and I ended up taking a load of pictures with really high ISOs. Anyone who knows photography, I was taking pictures at 32,000 ISOs, and normally they would be unusable. And they've come back perfectly usable once I processed them with AI. So it's amazing what it can do, and I'm sure it will get into the radio market. I think at the moment, amateur radio is a relatively small market if you look at it compared to all photography market worldwide, etc. So it might take a little while to get, and it'll probably need enthusiasts to generate it. But there's plenty out there who will get involved and do it, I'm sure. Any more? No? No, I think that's it.
Well, thank you very much, Mike.
Right.
I think you made a very complex subject very simple.
I hope so.
And
That's
I
the
think
idea.
particularly and brought it into a very practical arena as well. So I think we should show our appreciation.
Okay.